Hello. Okay. Test. All right. Do you recall this exercises? This is practice on your own, E2 elimination. And I was mentioning that there's an stereochemical or conformational requirement that it's embedded in some of the examples that we were doing. And the first thing I hope you guys were able to do is to locate the beta hydrogens. And I hope that in the first example, you were able to locate two beta hydrogens. And if you are to remove those by the effect of base, you would end up with these two alkenes which turn out to be identical. In this case, it does not matter whether you remove this hydrogen or this other one, you would get to the same exact product. Now, in the second example, however, that's a little different. And you will be able to recognize, now we have two distinct beta protons. And beta hydrogens referred with respect to the halogen atom, the leaving group. So if you recall, this is the alpha position, and these are the beta positions, and we have two of those. And so there's two possibilities of getting HX elimination, whether we eliminate the one that I'm going to denominate as 1, H1, or H2. Now, which hydrogen should we have to eliminate to get the product in the first box? H1 or H2? Which one? H1. Yeah, it's clear. We form a pi bond between the carbon next to the phenyl and the alpha carbon, where the bromine was. So this results from H1 elimination. And the other one obviously results from elimination of H2. And this label is arbitrary. You can label them A, B, C, 1, 2, 3. It does not matter as long as you keep track of which ones are the ones you're getting. Now, there's a stereochemical requirement that I keep mentioning, and let's talk about it because this is extremely important aspect of an E2 reaction. And an E2 reaction is a stereoselective reaction. What is stereoselective? Stereoselective means that it preferentially gives one stereoisomer over the other. When there are possibilities of forming stereoisomers, and having gone over chapter 5 at length, I expect all of you to understand what a stereoisomer is. One stereoisomer is preferentially formed over the other. In this particular case, we have two different alkenes, trans and cis. Well, the trans isomer is being measured. Now, what is the relationship between these two isomers? Are they enantiomers? No, because they're not non-superimposable mirror image. But what are they? First of all, do we agree that they're stereoisomers? Yes, they're stereoisomer. What kind of stereoisomers? That's the easy peasy way to go. But if we want to go for IUPAC um, classification. They're diastereomers, remember? They're stereoisomer that are non-mirror images of each other, but geometrical isomers perfectly fine as well. They're just trans and cis alkenes, but they're diastereomers. Now, why is it that the trans is the major and the cis is the major? We have a number of factors that contribute to that observation. This is an empirical observation, and this has been found to be the case in all E2 elimination, and it has to do with a number of factors. Of course, you know at this time that product stability is a big factor. And you know about the side-step rule. What does the side-step rule says? You would form the what? What type of alkene? And the most substituted is going to be formed because of? She would form the most stable alkene. But also, it's not only about relative or degree of substitution, but we also know that the trans is more stable than cis. So that in its own right, it's giving us a clue as to why is it that the trans is being formed preferentially. But that's not the end of the story. If you were to ask me, I would say that probably is a minor factor that contributes to this observed stereoselectivity in the E2 elimination. In my opinion, and in the opinion of most organic chemists, the reason why the E2 reaction is stereoselective has to do with the transition state. And in particular, with transition state stability. And there's a conformational requirement that I'd like you to learn this new word, anti-periplanar arrangement of H and the leaving group. Let's explain what that means. This is the main reason why the E2 reaction is a stereoselective reaction. Let's explain what I mean by anti-periplanar. If you have this particular alkyl halide, I have generic substituents R1, R2, R3, R4, H, and Br. Notice how I'm using wedge and hashed lines and solid lines to indicate I have a hydrogen in the same plane as the carbon, as in the same plane as the alpha carbon. This is the beta carbon, this is the alpha carbon, and also in the same plane as the bromine atom. All four atoms, 1, 2, 3, 4, are in the same plane. And on top of that, the bromine atom is in the opposite side of the hydrogen atom. This conformation right here is called anti-periplanar conformation. And I want you to remember this and know how to draw this anti-periplanar conformation. There's a couple of ways to do it, and this is an easy way. You simply do the zigzag skeleton, and then you arrange atoms up and down in one carbon, up and down on the other carbon, or not up and down, but to the front and to the back of the plane of the paper, to the front and to the back, and keeping all those four atoms in the same plane. Hydrogen, beta carbon, alpha carbon, and halogen atom. All of them are in the same plane. Now, what is this, the drawing here that I'm trying to do? How is this projection called? Newman projection, perfectly. So this is another way of seeing how anti-periplanar conformation is arranged. So I have a half-filled Newman projection, and we're looking down beta carbon, alpha carbon. And this will be the beta carbon, and so this will be the beta hydrogen. For that anti-periplanar conformation, I'm going to ask you to guide me. What should I put down in this box? Bromine. And so that right there, this fact right here, that they're 180 degrees from each other, this is why they're anti-periplanar. That's why we call anti-periplanar. So anti, everybody gets why anti, right? They're 180 degrees from each other. But periplanar, what does that mean? Yeah, yeah, easy peasy, right? Logic. So hydrogen and bromine are in the same plane, and they're 180 degrees with each other. Now, this conformation is more stable than the following one. In this other conformation, H and Br, they're not anti-periplanar, but they're syn periplanar. And this is a less stable conformation when compared to the anti-periplanar. Why is it so? Why is anti-periplanar conformation more stable than syn periplanar? And this we know since the beginning of our discussion of conformation of alkanes. Eclipsed, staggered. Which one's more stable? Staggered, right? And that's what we have here. And so now let's complete our Newman projection from above. What do I have to put here in the box on the left? I already put a bromine here. What do I have to put here in the box on the left? R3. Everyone agrees? Remember, we're looking down beta carbon, which is in the front, alpha carbon, which bears the bromine and it's in the back. In the box on the left, on top, what should go there? R3 or R4? It's one of the two. Say it again. Who says R3? 1, 2, 3. Who says R4? Okay, explain. Someone who says R4, explain why. Perfect. That's it. So we're looking, this is our eye right here. We're looking down carbon, the beta carbon, which is the one in front. It's this one where the hydrogen is, and it's up. The bromine is down on the beta carbon. R4 is on the back of the plane, so it should be on our left when we switch our molecule. So this should be, you have to learn, you have to practice how to do this. And so this would be R3 and R4 and R3 on the right. Everybody can see that now? Perfect. Now, let's practice the results of this stereochemical requirement. But before we do that, I want you to please, in terms of arrow pushing, to know, what do we know about this reaction again? Is it stepwise or not? No, it's a concerted reaction. It's a single step. So in terms of the arrow pushing, Your arrow pushing should start from the base, in this case stereotoxide, removing the beta hydrogen. The lone pair, sorry, not lone pair, the pair of electrons that it is in the bond, it's going to go and form the new pi bond, and you're kicking out all at the same time the leaving group, and you're forming an alkene. So I want you to become an experts in how to draw this concerted reaction. All bond breaking and bond making events are happening simultaneously, not stepwise. So it's very similar to an SN2, in which you have a transition state, which is trigonal bipyramidal. In this case, we'll show how a transition state looks like for this one, but it's also one transition state only because it's one single step. Is that clear? Perfect. Now, let's look at the results of this anti-periplanar requirement in the isomers that we would get in alkenes. I have this hydrogen atom and this bromine atom, they're anti-periplanar, correct? Everyone agrees? Everybody can see that? Perfect. Now I have phenyl towards me in front of the plane or above the plane of the paper. This other phenyl, it's also on the same side. These two phenyl groups are on the same side. So the question is, what should I write in these boxes? So we agree that we're going to remove HX. These two should be gone. So we're going to end up with an alkene in which one carbon is going to have a phenyl and a methyl. I have it right here already. The question is, what is going to be in the other side, and where? Where does the phenyl should go? Next to the methyl or next to the phenyl? And I'm going to call it phenyl 2, just to differentiate it from the other one. Although we don't have to do it in this case because one is attached to a carbon with a hydrogen, another phenyl is attached to a carbon with a methyl. But just so we know what we're talking about, this phenyl group, where should it go in the product? Top? Why? Okay, so do we always form E alkenes? So when there is a possibility to form cis and trans, yes, sure, we're going to form the trans because it's more stable. But this is exactly why the E2 reaction is stereoselective. Notice, phenyl groups, they were on the same side, right? In this arrangement here, for the hydrogen and bromine to be anti-periplanar. This is the transition state. The T-butoxide, we have dotted lines picking up the hydrogen, dotted lines breaking that bond and forming the new pi bond, dotted lines breaking the carbon-bromine bond. And this will give rise to this product. Now, if we have the phenyl groups on the same side, then we just put them on the same side. And this will be an H. Does that make sense? If both phenols were above the plane of the board, then you don't have to break your heads. You just simply look, okay, this phenyl is above, this other phenyl is also above the plane. So they're going to end up on the same side. Both were above the plane. So in the alkene, they end up in the same side. Okay? Cool. Now let's do the opposite. Let's try the other possibility. Do I have H and Br anti-periplanar? Yes. So H and Br, they're anti-periplanar. We can check that. Fine. Now, we know that we're going to remove H and Br, so we might as well just draw the alkene, and we can do this arbitrarily. I just chose to put phenyl at the bottom, methyl at the top. You can do it either way you want. Just keep track of what you have in your molecule. Now, this phenyl and methyl, it's this carbon right here. Now, the other carbon, it's going to have a phenyl and a hydrogen, much like the other case. Now, the question is where each of these is going to end up. And again, we look the transition state. So what is on the same side or on the same plane of the paper? This would be the transition state, delta minus. We have phenyl and what else on the same side? H, right? So then it's easy peasy. We put an H in the same side of the phenyl group. And on the other side, we put the phenyl. Is that clear? Yeah? No, you have to arrange. So if you want to make an E2, you have to arrange the conformation to an anti-periplanar. And let's remember, this is a conformation. This one right here, the starting material, the alkyl bromide, I drew it in a particular conformation. Remember, the sigma bonds are freely rotating all the time. And so it's not going to be frozen in this conformation all the time. And we're going to see the implications this have for substituted cycloalkanes. But if you have t-butoxide, it's kind of rare that you were going to have an SN2 because t-butoxide is very bulky and it's highly basic. But if you don't have an anti-periplanar arrangement, then there's no possibility for E2 elimination, or the rate is going to be very, very small, very, very slow reaction. And so in those cases, possibly an SN2 is going to be favored over an E2. But the requirement remains. This stereochemical requirement, or if you want, conformational requirement, probably is a better way to depict it. Conformational requirement of anti-periplanar groups is the reason why the E2 reaction is stereoselective. Okay, so now let's see how that plays a role in substituted cyclohexanes. And this is where your knowledge of chair drawing and conformation comes into the picture. And you have to be very much ready to draw chairs and to say which of the chairs is more stable, and to be able to depict which hydrogens are able to be eliminated. And so let's compare two stereoisomers, cis methyl bromocyclohexane versus the trans isomer. First of all, we need to be able to draw the chair properly. And for that, we need to be systematic in our approach. And we need to you can start arbitrarily, but be systematic and take the proper precautions so that you know that you're doing the chair flipping correctly. Okay, so I'm just arbitrarily select this carbon to be the carbon on top or in the corner of my cyclohexane. And then I need to keep counting. This is 1, and this is 2, this is 3. So I'm going counterclockwise in my counting. I just need to be consistent. 1 and 2. And this would be 3. It's very easy, and I've seen this numerous times, over and over and over. You start with a particular chair, and once you do a chair flip, you swap the order of substituents, and then you end up with a different stereoisomer unintendedly. And so I'm giving you the tips so that you avoid that. Once you arbitrarily select, okay, this is going to be my carbon 1, my carbon 2, and my carbon 3. Remember, this is a top view, so don't change anything. Stick to that arrangement and to that and to the assignments that you made. So then, once you do the chair flip, this is going to be what carbon? This one right here, according to my arbitrary assignment. That's 1. It shouldn't change. Which one is carbon 2? Remember, I started going counterclockwise. So I need to keep that consistent. Where is carbon 2? Is it this? No. Perfect. But a lot of times I've seen people changing substituents and doing that. That's a mistake, and you will unintendedly be drawing an incorrect stereoisomer. This is my carbon 2. And it's not that I care the numbers right now, but I'm trying to give you tips and tricks not to make mistakes when doing chair flipping. This is carbon 3, correct? I didn't change anything. So from the top view and the side view, if you will, I kept everything consistent. Carbon 1 with my halogen, and I went clockwise just to keep consistency. Okay, so if there's cis, and if I chose this bromine to be axial, if they need to be cis, the methyl should be axial or equatorial? Equatorial. If I were to put the methyl axial, they won't be cis, would they? They would be trans. So we need to be able to draw that correctly. Okay, now you will see why I'm drawing chairs to begin with. You might be asking yourselves, what do we care about chairs? Well, you have to care a lot, and you'll see why. Now, let's do the chair flip, and now let's see, okay. Now, after the chair flip, if our bromine was axial, it should be equatorial. If our methyl was equatorial, now it should be axial. And we should all know how to do that chair flip at this stage. Now, let's identify our beta hydrogens, the ones that we can eliminate. So, very conveniently, I have one right here. This is our beta hydrogen. And what do you notice in the conformation? Are they anti-periplanar or not? We're going to look down carbon 2 to carbon 1. We're going to put our eye, and we're looking down this way. What is here on top? This is carbon 2. On the back, we have carbon 1. What do we have here on top? Bromine. I hope you're able to see that. Now, our methyl group is this one right here. And so right here we can see that these are cis, right? Now this beta hydrogen is anti-periplanar. And so this is ready to be eliminated. This conformation can eliminate. Now, how about the other one? How about the other one? Can we eliminate this? This is not anti-periplanar with the bromine. And so we cannot say that we're going to eliminate that particular hydrogen. What else? But if it's not that, how do we have any other beta hydrogens? Okay, we have one more here, and if you want one more here. Neither of these two is anti-periplanar. So it does not eliminate. In other words, the only conformation able to give you an E2 elimination is the one in which the bromine or the leaving group is axial. So as soon as you have substituted or cyclohexane, you have to put your leaving group, your halogen atom, in the axial position. If it's not in the axial position, it's not going to have any beta hydrogens that are anti-periplanar. And you can try as much as you can to draw Newman projections of these other beta hydrogens. And you will see that neither of this, not this, nor this one, is going to end up anti-periplanar to the halogen atom. You try on your own and you will see that it's not possible. The only way for that to be possible is that you set your halogen atom in the axial position. And only after that, check which hydrogens are able to eliminate. And I drew one here, but do we have one more that is anti-periplanar that I haven't drawn? Yes, where is that? In the other beta position, right? This one right here on the back. Do you guys see that? This is also anti-periplanar to the bromine atom. Now, based on CHM rule, if we eliminate, let's put this 2 and 1. If we eliminate 1, we are going to get this alkene. If we eliminate 2, we're going to get that alkene, right? Are you able to see that? Now, which one is going to be major? Tri-substituted alkene or di-substituted alkene? So this is going to be major. And how do you know it? Two reasons. CHM rule, of course. And how were you able to determine which one, which hydrogen or beta hydrogen gives you which one? By drawing chairs. So now you know how important it is to draw chairs and identify beta hydrogens that are able to undergo eliminations. In this case, there's 2 possibilities. One would give you a major product. A second one would give you a minor product. But in all cases, the bromine atom has to be axial. And only then you look for anti-periplanar hydrogen atoms. Now let's look at the other example where we have the trans stereoisomer. I wanted to keep things constant, and so if I chose this methyl to be up, I stick to the same system in which now the methyl here was also up. So I wanted to stick to the same system that I chose on top. Now my bromine atom, it's also the same. Instead of being axial and syn to the methyl group, now it's equatorial. Now bromine and methyl, are they cis or trans to each other? They're both equatorial. I hope we can all see that. Yes? Are they cis or trans to each other? In other words, did I drew the correct chair? The ones that are trans would be these two hydrogens. These two hydrogens are trans, and they're both axial. And remember, when you have one equatorial going up, the equatorial next door is going down. So they're also trans. So I drew the correct chair. They're both trans. So far, so good. Now, can I go ahead and look and start looking for which beta hydrogens I'm going to eliminate here? No. Why? Bromine is not axial. We know that's a requirement. So let's do a chair flip and let's see where we end up. So after the chair flip, again, do not switch or swap the carbons with substituents. And we're going to stick to this being number one, this being number two. This is just arbitrary. You can put A, B, C, whatever label you want. The carbon with the bromine is 1. So this is 1 right here. And I'm going counterclockwise. Number 2 is the one with the methyl. So now I have 2 is going counterclockwise, the one with the methyl. And so if the bromine was equatorial, once I do a chair flip, it's axial. At this point, everyone should be an expert in doing chair flipping. Now, if the methyl was equatorial, now it's axial. But I don't care about the methyl, I care about the beta hydrogens. So is this hydrogen beta hydrogen or not? There's one right here. It is a beta hydrogen. It is it's in the beta position, right? This is a beta hydrogen, but it's not antiperiplanar. So it cannot eliminate, even though it's a beta hydrogen. How about this one? Is it a beta hydrogen? Yes. Is it antiperiplanar? Yes. It's antiperiplanar to bromine, right? So it can eliminate. What is the product here? I hope everyone can see that. And this is the sole product. There's no other product that can be minor or major. That's the only one. Why? Because there's only one beta hydrogen that fulfills the conformational requirements of being anti-periplanar. And so the transition state would look something like this. So we have to draw our chair. And we have to draw our base. And this is the pi bond, the new pi bond. And so you see how we have a pi bond. Next, we have a methyl group, which remains untouched. And so this is the sole product right here. And so I kept the same nomenclature. If methyl was up, like here, this will be the top view of the product. But if you want to have like an extra safety device to make sure you don't make any mistakes, then you simply draw this transition state, and maybe you can put a little chair that it's not going to be the real way to do it. But now you remove the bromine and you make a pi bond here, make a double bond, but everything else remains the same. The methyl groups still goes up. And then you transform this into the top view, or the planar representation of that particular cyclohexene now. This could be a good safety device for you to keep track of. Nothing happened to the stereochemical center here, the stereogenic center at where the methyl was attached. Okay, is that clear? And nothing short of practicing on your own will get you ready to rumble and being able to ace the exam. And so I would like to give this for you to practice on your own and to draw the chair conformations of that particular substituted cyclohexene. I'm going to scan this and upload it. This is going to be the last page of our lecture notes. And please go on and on your own have to draw both chairs, identify all beta hydrogens, and then also identify which of those beta hydrogens are able to eliminate. And in which chair. And after that, only after you've done that, then you're going to come up with major or minor products, if there's any, or whether it's a sole product obtained. And you have to draw the structure. And remember, you have to be systematic in your chairs. Consider this a top view. Once you put it in chairs, stick to what your system is. Consider this top view, your chair side view, and keep going. If you start numbering clockwise or counterclockwise, remain that way across the board.